When we consider equilibrium reactions or reversible reactions, important to note that nothing changes. So everything stays the same. There are nothing new in the way that we are going to model our reactors, that we are going to describe our energy balance for adiabatic, non-adiabatic reactors. Just like the previous theme, parts of theme 5, when we consider the energy balance. But what we need to consider is the impact of the equilibrium limitations and the temperature dependence, especially for exothermic reactors, when we make design decisions. So the thing that will be different is the algebraic equation for our rate expression that is needed to complete our energy and our mole balances. And for the rest of the video, we are going to consider a very specific reaction, the simple isomerization reaction. And we are going to assume that we've got pure Fa0 that is fed to a reactor. At this stage, any reactor, so non-specific, that we need to process. And that this is therefore the elementary rate expression of that reversible reaction. So we've got our forward rate constant, we've got our reverse rate constant. That is a combination of the forward rate constant divided by the equilibrium constant at the temperature that we are busy considering. So in our rate expression, we've got our normal concentration dependence. Of course, we can write that as a function of the conversion of A, and if we know the volumetric flow rate, and based on our pure A inlet condition, we can also use the reaction stoichiometry to calculate the concentration of B as a function of the conversion of component A. So in addition to these two concentration effects, we've got two temperature-dependent parameters in our rate equation. So first, of course, the Arrhenius temperature dependence of our forward rate constant that also forms part of the reverse rate constant. So with an increase in temperature, an exponential increase in this rate constant. In reversible reactions, we also have to contend with the temperature-dependent equilibrium constant that forms part of our rate constant for the reversible reaction. So in this course, we will always assume that we can use Van 't Hoff's equation to describe the temperature dependence of that equilibrium constant. And what we need is a value for that rate constant at a reference temperature, which will allow us to calculate Kc at any other temperature, either in our PBR, PFR, or as it occurs in our CSTR. So you may want to go and revise the Van 't Hoff equation, but the main assumption of the Van 't Hoff equation is that del H of our reaction is not a function of temperature. So of course at this stage we know that is only true if del Cp of my reaction is pretty much equal to 0. So how we are going to attack it in this course is we are going to assume that even though there is a slight difference in del Cp reaction, when it comes to calculating the equilibrium constant, it is suffice to ignore its effect on the Kc value. What we want to do first is for our given inlet concentration conditions with our given inlet molar flow rate of A and Q0 value, we want to determine what is the maximum possible conversion in any reactor as a function of a varying temperature. So we want to evaluate for a range of possible operating temperatures. How does my equilibrium conversion change? And we've got two approaches in which we can calculate that. First, by using the Kc equation, where we say Kc is the product of the concentration of each of our components in the reactor raised to their stoichiometric number, which will be that equation for our specific reaction. Or we can use the fact that at equilibrium, there will be no macroscopic change in composition, and therefore our rate must go to 0. And if we then make x the subject of that equation, we can derive an equation for x equilibrium as a function of our temperature-dependent equilibrium constant. Of course, if I now said that there's some FB naught also being fed to the reactor, this concentration over there will have a different value. So it's going to be FB naught plus FA naught times X. Or if I have a different reaction with a different rate expression, I'm not going to necessarily be derive this shape of the X equilibrium versus temperature equation. But nonetheless, you should be able to get a value for equilibrium conversion by setting this rate equal to 0 as a function of temperature in your reactor or along the way in a PFR reactor. If we now substitute our Kc equation, temperature dependence, and we choose a range of temperature values, so we choose, let's say, from 298 to 1000 Kelvin, Lorentz space values, and we calculate the Kc value for each of those temperatures, we can calculate our equilibrium conversion, and the result will look somewhat like this, qualitative drawings that I've made over here. For an exothermic reaction, as I increase the temperature, of course, I will see that I can obtain a lower equilibrium conversion given my inlet conditions, and for a colder temperature, a higher in equilibrium conversion. Of course, the opposite true for an endothermic reaction. Higher temperatures, higher conversions. So now that we have established our thou shalt not pass line for our given inlet conditions, and remember this is not dependent on the reactor type or any energy balances yet, and for the exo or the endothermic version of our reaction, we want to superimpose our energy balances first for any adiabatic reactor on these figures. So this linear shape we could derive regardless of whether it was a CSTR or a PFR, or PBR reactor. This linear equation, of course, results if we assume that del Cp of our reaction is pretty much equal to 0, which is our first approximation that we are going to attack, and that the Cp value of each of our components here does not vary with temperature, so we are going to use average values for Cp values in this energy carrying capacity. So pause here and make sure that you can derive this specific shape of our adiabatic energy balance for our reaction that we are busy studying. So A goes to B when we have pure A and different temperatures for T naught as our inlet temperature to whatever reactor we are going to choose. What is noteworthy here is that as I increase my T naught value and I construct this figure, this is the absolute maximum conversion for T03, for instance, that it's possible in an infinitely large reactor. So you can have a reactor as big as a building as engineering 1 or in 2 engineering 1s, and this is the maximum conversion that you will be able to achieve in any adiabatic reactor. If you start decreasing your inlet temperature, that maximum equilibrium conversion is going to increase for an exothermic reactor. I can observe the same kind of behavior in an endothermic reactor, but here as I increase the temperature, adiabatic operation, so therefore of course the slope is going to be the negative slope over here, and I can see for an infinitely large reactor, this is the absolute maximum conversion that is possible, whether you have a CSTR or a plug flow reactor. If I'm now interested in solving this specific limit, so I have a given inlet condition, I've got an adiabatic reactor, and I want to determine this maximum X equilibrium, temperature equilibrium combination. Of course, I've got two unknowns. I've got temperature and I've got conversion, but I also have the equation that describes this line that I previously derived. So there is my X and temperature hidden here in my Van 't Hoff equation, but I can reduce it to a two unknowns, two equation kind of problem that I can easily solve using FSolve. So my recommendation when you implement this is to rather solve only for the one variable in this trial and error FSolve kind of procedure. So you will provide a guess value for X. Use the linear like energy balance to solve for temperature in your function. And with that temperature that is at least associated with an X value, calculate the very non-linear Kc values. And then you use this equilibrium x equation as your return function that f solve must get equal to 0, of course, provided that you now write it in the correct form. It is important to note that once we have now established that maximum possible adiabatic conversion, that we will never design a reactor to actually operate at that limit. First off, it will need to be infinitely large because the rate there goes to 0. And even if you're very close to that equilibrium line, the rate becomes so low that added conversion does not justify the extra volume or mass of catalyst in your reactor. So generally, a rule of thumb is that you will limit your conversion to 90% of your possible equilibrium conversion when you are busy designing reactors for equilibrium reactions. We are therefore more interested in what's happening to the rate here on the way to equilibrium when we are specifically going to consider the decisions we have to make in order to optimize our design. For that purpose, we now want to evaluate what happens to our rate just as a function of x and temperature as I follow this adiabatic line. And first we're going to consider an exothermic reaction. So of course, yes, we have this decrease in reactant concentration that will lead to a decrease in the rate. But initially, I have no component B present. So I have this decrease in concentration, but I have an exponential increase in concentration of my Arrhenius rate parameter. So for Arrhenius, what is important to note is that there will always be an increase with an increase in temperature. So remember, this is the inverse of temperature. So this is warmer and this is the colder side of your figure. And over here, I've plotted ln K, increase in temperature, exponential increase in that K value. That will result in an increase in the rate. So as the reaction proceeds, you form more of component B and the rate of the reverse reaction becomes more significant. And there, of course, you also have the Arrhenius effect that will increase the rate constant of your reverse reaction. But you also have the effect of the temperature on Kc. And for an exothermic reaction, we've got the opposite effect to Arrhenius. So as I increase my temperature, I'm going to decrease this denominator over there, and I'm going to further increase the rate of my reverse reaction. We can visualize this effect if we now, for instance, consider an inlet temperature of T01, and as I have a reaction that proceeds and the temperature is going to increase, I will see this initial increase in the rate on my Levenspiel plot. Reverse reaction starts to take over and the effect of temperature and loss of concentration of reactant until I've got this very sudden decrease in the rate as it goes for this asymptote where the rate goes to 0 and 1 over the rate wants to go to infinity. You should notice that from the shape of this graph that this asymptote is approached at the equilibrium conversion that corresponds to the equilibrium conversion that you discovered by solving simultaneously for both these equations. For an endothermic reaction where the temperature is going to decrease along this adiabatic energy balance line, for my forward reaction, Arrhenius with a decrease in temperature, Arrhenius line over here, the slope depends on the activation energy divided by R, of course, and this decrease will be observed with a decrease in temperature. The same decrease, of course, will occur for the reverse reaction. However, the denominator here, my Kc, will also decrease with a decrease in temperature. So decrease with a decrease in temperature here, meaning that the effect of temperature is not so significant on the reverse reaction. But all effects of temperature and concentration of the rate of an endothermic reversible reaction implies that the forward rate will continuously decrease as I increase the conversion. So I will not have this initial up to the maximum. I will only see a decrease up to this asymptotic point where my rate becomes 0. So, of course, for an adiabatic reversible reaction rate expression, it's possible to see that this will definitely be a maximum in the rate again, for which that range, if you want to design this optimal reaction train, choose a CSTR followed by a PFR to complete the rest. And of course, the rest, meaning if you go to infinity, even though that is just going to follow that line, it's still going to result in an infinitely large area. So you will stop somewhere before you reach that equilibrium asymptote line. So advice when you employ this in Python is when you now want to construct a Levenspiel plot to see what happens to your rate, is rather just have a straight plot of the rate as a function of conversion. If you now, for instance, choose an X range of values between 0 and 1, somewhere in the middle of that range, it's going to hit the point where the rate goes to 0, and then you've got a situation where you have to divide by 0 in that rate in order to construct the Levenspiel plot. That will not happen when you calculate that rate. So if you choose X anywhere, you can calculate for each X, you can calculate your temperature, and that temperature line is not going to stop where it says it must stop, remember, so it's going to just go all the way to the X is equal to 1, and for each temperature you'll be able to calculate your parameters, and for each X you'll be able to calculate your concentration, and therefore you'll be able to calculate your rate. And if you now plot that, you will find that you can see where the rate goes to 0, so that is actually your equilibrium conversion in your reactor. So this may tempt you to think that this is where the reverse reaction will take place, but no. Your reaction will stop in your reactor there. So it's not as if you are going to see a decrease in your conversion suddenly because the rate becomes negative. So this is just not a feasible part of the line. It passes the thou shalt not pass their line, and Python doesn't know that it's thou shalt not pass, so it just continues happily and it can still do the math. But in real life, the reaction will stop there unless there's a disturbance in the temperature, so you have some cooling there, or you introduce a side reaction, then something can shift and I can move past that equilibrium point. So in order to see whether you understand, I want you to consider this following question where you actually have a plug flow reactor. So now I specify a specific reactor type. It is operated adiabatically, so now heat can flow to or from my reactor. And I have different possible inlet temperatures, 0.1, 0.2 or 0.3. And I have my FA0 in the feed stream. And along the length of the reactor, for the 3 different possible scenarios, so in reactor 1, in reactor 2, and in reactor 3, where I have the 3 different temperatures, I would like you to, on the same axis set, draw a qualitative figure of the shape of X of A as a function of the length of my reactor, length or volume or mass, but the shape of that X figure will remain the same. So I want you to think about what is that slope of that line? What does it tell you? Where is it going to start? How is it going to look in the middle? And where is it going to stop?